Hello and good day to all of you that have joined us. My name is Jon Laughner. I'm with Penn State, representing the TOPCORP group of oil and gas training and workshop. We thank you for joining us. And as we do just a few introductions here, thanks for taking the time out of your day to be a part of this. We're thrilled to have Dr. Lanny Schoeling with us with a fascinating topic. I think you'll find if you're here, I'm sure you're here for the same reasons. So we're appreciative of him taking his time. As you come in this today to join the webinar, we'd love to hear who's with us, where you all from, maybe even a little weather report, what's going on in your part of the country. If you wouldn't mind doing that down in the chat pod. And just to keep things nice and complicated and unorganized, as we go through, or as Dr. Schoeling goes through his presentation today, if you have a question, if you would go down to that Q&A area and list it in there, we'll try to get as many as we can towards at the end of the presentation. And Dan, if you'd go to the next, please. So today's webinar is sponsored by TOPCORP. We train regulatory oil and gas field inspectors. Many of you have been participants in the past, and we've enjoyed this experience. Next, as we do that, we've done a fair number of regulators across the country and Canada. And go ahead, Dana, if you would please, to the sponsorship page. And we couldn't do it without the people that and the companies that sponsor and fund TOPCORP, Top Energy. And you'll see there's industry, there's NGOs, there are other firms that are associated that have been a part of TOPCORP and provide funding to make it all happen. And we certainly appreciate their support. Next one. And so we do the webinars as part of our outreach to oil and gas regulators. We attempt to do these about every quarter, and our goal is to have something new and on the cutting edge of the industry to provide to you so that it makes it a worthwhile professional development opportunity. We do record these, and it'll be made available to you later if you would like to share this with somebody else that wasn't able to be a part of it. Oftentimes we have people that register for this and can't attend at the moment, and you'll get an email, even if you aren't here, but you'd registered to be able to view it later. With that, we'll go right to the next and do our introduction of our guest speaker today, and that's Dr. Lanny Schoeling. Lanny is the president of EOR Consulting, LLC. Lanny has over 40 years of experience in many technical and managerial positions. He's currently president of EOR Consulting and vice president of oil field innovation at Neotech Energy. Prior to this, Lanny was vice president of engineering and technical development for Kinder Morgan CO2 company and chief reservoir engineer for unconventionals at Shell E&P. He holds a doctor of engineering and petroleum engineering and a master's in chemical engineering. He's a professional engineer in Texas and Kansas. He's a member of the Society of Petroleum Engineers and was a distinguished lecturer in 1996 for SPE and is the author of numerous SPE papers. In 2016, he was awarded the SPE IOR Pioneer Award at the IOR conference in Tulsa, Oklahoma. He is the co-inventor on over 20 patents. Recently, he was appointed a Texas member of the Interstate Oil and Gas Compact Commission by the state of Texas. Lanny is also on the Distinguished Lecturer Committee, which selects future SPE distinguished lecturers. And before I even go on to the introduction of your presentation, Lanny, I just want to say how much we really appreciate you joining us and taking the time to provide this and share your expertise. And I know depth of knowledge involved here. And with that, I'll just say that I know that Lanny's presentation today covers the principles of carbon capture and carbon capture flooding, which are based on his extensive research and practical experience in the industry across North America and internationally. This webinar will focus on the reservoir, well design, and surface facilities. Of particular interest, he will discuss the screening of locations and the economics, including the USA 45Q tax credit incentive. With that, Lanny, I'm going to turn it over to you and welcome you and thank you for being here. We look forward to your presentation.
Thank you very much, John. Yes, and it's an honor to be here. As we say at SPE, and it's behind me here, motivate, inspire, and educate. And that's what today's all about. And I just hope you guys all leave here with understanding what CCUS is and CCS is. And we just have a lot of fun too. I mean, that's what it's all about. I'm going to hit the share screen here. And okay, this is the title, and John did such a good job. I don't think I need to, but here is my, and you will get a copy of this. Well, yeah, I can arrange you can get a copy of this, but yeah, here's my email, and that's my phone number. If you guys want to ever call me and find out what, if you want to talk about it more. Okay, I was supposed to be able to move the screen. Oh, there. Okay. Now, here, let me get rid of that. Okay, the agenda today. And like, again, I want you guys to know, and when we're done here, if you don't know a lot about CCUS and EOR and CCS, then I haven't done my job. And I want to do my job. And I want to show you where the CO2 sources are. We're going to talk about that a little bit. And for implementation of carbon capture, what we have to do and what we have to look at, those sort of things. I'm going to show you the current pipeline structure for CO2 right now and where we think it's going. There's some great work out there in CCS and CCUS that are talking about what the pipelines could look like in the future. And then I'm going to talk about seeing, like John said, 45Q. I'll talk a little bit about it, and I'll talk about the Class 2 and the Class versus Class 6, just a little bit on that, so you guys are very, you're knowledgeable in the area. And then how do you go about implementing one of these projects? I'm going to lay out a roadmap, and then we're going to go through a little bit of the screening and have some fun and determine economics and talk about it. And it isn't always a slam dunk by no means. There's work here. Okay, the four carbon components that you need. I wanted to go back there. Wrong one. Yeah. So you have to have sources. That's important, and that usually comes from a lot of fertilizer plants are out there, and ethanol plants are out there, and they provide CO2 pure, which is really nice. But most of it, and we'll talk about it, is natural gas processing. I just finished a project on the other side of the earth internationally, and it was a natural gas processing. We have the same thing here in the States, and I'll show a Exxon Valdez is a natural gas, and so most of the CO2 we get is actually produced with natural gas, and it's been going up in the air as an emission, and we want to carbon capture that and put it in the ground, and so that's what we're looking at, and it works, and then there's what we like to do is what I like to do, what I've done all my life is put CO2 in the ground and make carbon come back out too, and try to make it a zero emissions, total emissions out in the total climate, in the total life cycle. And then you got compression and separation equipment. That's very important, and that depends on the size of your source and the rate of your source on how you develop that. You also have what we like to do is take all the water out of it, and so we have dehy units, we call it, and that cleans it up so it can go down a pipeline, which is our next so it can go down a pipeline, and it can be just a pure steel pipeline, because if there's no water in the CO2, it will not corrode, and that's a nice thing to have anyway. But then I'll talk about if you have water in the line, what kind of metallurgy you need to change to today. Also, CO2 sinks. This is it. And this is what we're going to put it in the ground with wells, and there's different processes. We use oil and gas fields, and then you can go in and just put it in saline fields, which is your Class 6 projects. And I'll talk a little bit about that. Here's just a little bit more of another diagram, putting that in more detail. We have here again, carbon-based fuel coals right here. They're probably the biggest, but all over, I mean, especially here in Texas, I just drove to Florida along the coast, and there's all kinds of facilities that are making us products we need for our to live in the kind of standard of living we're living in. But CO2 is being put in the air, and what what's great about it, and actually Exxon's been pushing this, which I really enjoy hearing about their project. They're going and what they're going to do is put it in the ground way underneath the ocean in the Gulf. And there's some projects that they're looking at there, and that's CCS. And so this is happening, and it's an exciting new field. I mean, it's awesome. Here are the CO2 sources we have. And they here again, a variety of them. Cement plants, believe it or not, produce CO2. And of course, ethanol is one of our biggest, and fertilizer you saw me earlier. But we have CO2 sources all over the U.S. and in the Gulf even. And so this is one of, I think, will be one of the biggest CCS projects going forward. Will be right here, and it'll be going in the Gulf here, but yeah, underneath. That's what I think will happen. I'm not perfect in my predictions, but I think there's going to be a lot of that going on, and it's going to go on throughout the United States. It already is. There's a number of Class 2 projects that are under the 45Q in Class 6, and so in here you got your annual CO2 emissions. You can see just from the size of these here bubbles on how much is being emitted. And this can be eliminated or minimized by carbon capture. And that's what this talks about. This is just one draft national security prediction. And it's done by the Regional Carbon Capture Deployment Initiative. I wanted to show it because now some of these fields, some of these lines are already in existence. I'll show you that here later. These are all in existence. And there's a few over here that are in existence. Up here in Wyoming, we got some in existence. And up here, going into Canada, we have some stuff going on that they're carbon capturing and putting it in the ground here. But they're already currently existing. But this is kind of like what they see, especially here in the mid section. But I do think they're missing the coastals here, so they need to add those, especially in California. There's a lot of work being done in the California area, and then also the East Coast. So it's just really interesting. Here is the current pipeline structure, and it is and I talked about it, the Dakota Coal Gasification Plant, and it's producing, and they're putting CO2 in the ground in oil and gas fields. Up in Canada. And here, this is the LaBarge gas plant I was talking about earlier that Exxon did own. I don't know if they still own it. They probably do. I'm not sure. But then they go into these here oil fields up here, and they produce oil from CO2 injection. And then we have the traditional Sheep Mountain, McCampbell Dome, and Bravo Dome here that were natural gas CO2. Now, I think they will be huge in the future. Could be huge, also sinks for CO2. But then they went down here, and then where we have most of our experiences in Texas, and it's using. And what's great about it, and I'll be describing this, for a CO2 floodder to make money, he has to make sure that CO2 stays in zone and in where he wants to produce oil, make the oil miscible again and produce it. He doesn't want it to go out of zone. He doesn't want any of it, no molecules be emitted in the air. But I mean, things happen, but that's his objective. And it's worked for 50 years. So we feel pretty confident we can do this. And of course, ultimately, we talk about this, the CO2 will crystallize in hundreds of years in the right proper chemistry. Here is 50 years of experience. I just kind of wanted to go to it here. I don't know if you can see there and everything there. But what you have here is you have CO2 sequestration plant. You're going in and injecting it. It going through it doesn't immediately all retain in the reservoir, only probably about 30 to 40%. And then we re-inject it and we continue to redo that. But it's the net utilization that we can actually sequester. So if you have, and it's usually net is 8 to 10 MCF per barrel. And I'll talk about those metrics here later, and also some rule of thumbs that you guys can use from now on, so you guys can show your abilities with CO2. Okay, right here is just it's total capture capacity from 1970 to current. Now, I got this from a wonderful instructor at the University of Houston, It was about, but I think this was presented maybe a year ago, so it's probably been improved since then, but it kind of gives us a feel. We got this Century plant here, which is working in Texas, but I mean, you could go, there's the Shuck Creek field, and let's see, it's Shuck Creek, 35 miles northeast of Kemmerer, and it's in Wyoming. And like I said, the Century plant is operated by Oxy in Sandridge, and it's in Pecos County, Texas, too. And it actually sequesters 8.4 megatons per year, which is great. And then you can see the blue here tells you where our sources are, and this blue here is mostly gas processing, and that's what I described earlier and mentioned. And then EOR for sinking is mostly what we do for carbon capture at this point. What's great about it is it's low-hanging fruit because we have a revenue source because we can sell the oil by injecting the CO2, and we still sequester the CO2 the same. And then here we have another nice from University of Houston. And it came from a professor from there, and you can see the cost and what does it cost to remove the CO2 or sequester it? And you can see natural gas processing is a low hanging fruit. Also, biofuels to ethanols is low hanging fruit. But these are the kind of things that can be expensive. And then fertilizer plants are down there too. But then you get into the other like cement and these other, they're more expensive. And then of course, here on the right side of the slide, you have all of your carbon pricing by nation. And it's really interesting. We're in the middle there. Actually, the right hand is a little bit off on the bars, but this is the U.S. right here. And you can see the U.S. right there. But yeah, these are the carbon prices. Sweden is the highest. And here again, this was 2019, so we got about 3 or 4 years since then. So who knows where these numbers are now? But I'm just showing you internationally, this is a very prominent and worthwhile technology. Okay, these were these handy conversions and metrics I wanted to make sure you had, and like I said, I will make sure these slides get where John and Dana can get them to you. But the conversions really is, okay, when you see 1 ton in real metrics, that's 1.1 tons of CO2. And also 1 ton of CO2 is about, because we like to use English, or US metrics. And so 1 ton of CO2 is 19 MCF. And just to give you a feel for the scale of things, what we have is you have a small ethanol plant. You can get normally on a regular basis 8.6 MCF per day. Now, if you're going to have a small project like this, you need your source pretty close because you won't be able to afford to put a pipeline and all of that in. But as you get to the larger ethanol plants and get like 50 million cubic feet a day, you can then also see that, and then the metrics start going where you can have pipelines a little further from your, and you can go into bigger oil fields too. And then this is where I was talking about the net utilization. There's a net utilization and a gross utilization. Gross is when you're recycling, it's how many times you got to recycle. So it could be like 40 MCF per barrel of oil gross because you had to recycle so much to get. But the net is what stays in the reservoir ultimately, and that's why, like if a CO2 floodder was to purchase this from a plant or something, they look at the net is what they ultimately send to the operator, but then the operator has to recycle, and but then ultimately that's what stays in the ground is that net utilization factor. And I have 80 MCF there. It could be as high as 10, 11, or 12. That's not as efficient as we'd like, but it could be that high now because of capture, because of carbon capture, and it could be higher then because ultimately after I think a lot of these fields are done CO2 flooded, they'll just continue to put CO2 in them. Yeah, because as long as they know it, they can keep the plume where it needs to be, and they know for at least 100 years it's not going to go. And they got monitoring wells all around they could, yeah, that's in that most all operations I've worked at, they have all of these, even class 2 projects. So, I mean, and these are professional people that want to keep this CO2 in the ground. And here again, if you have the ADMCF, just kind of a handy scale, that's how much oil you'd recover. So let's just go for every million tons of CO2 sequestered. Oh, go the other way here. Okay, I just wanted to touch a little bit. So we're all, I don't know the audience if you've never been involved with CO2 before, but I kind of wanted to put us all on the same level. You just don't take CO2 out of the air and start pumping it in the ground. You have to put it into a critical, supercritical phase, which is your dense phase. And it has to be up then, and you can see here, it has to be up to over 1,771 PSIA and at a degree of 88 degrees Fahrenheit. And that'll depend. And this is your typical diagram for that. But when you're up above that, you have a dense phase, and it's no longer you have the transition of gas in liquid CO2 in the pipeline. And what's interesting, and that's what you want to pump it in. It's interesting is some of these projects that were early on that are low-hanging fruit, and one of the last ones I did internationally, we had to go in gas lines, which you can't get to those pressures. So, but you can get, which is nice about it, if it's large enough, they are pumping 2 phases down pipelines, which saves money and it makes these projects more economical. So you can then still do the carbon capture, and it's easy to do. And of course, and you got to go through, make sure it just, these pipelines need to have good integrity, and there's tests to do that. And you know that everything's safe, that you can do this. And okay, carbon capture. Yeah, this is something I got from the Carbon Capture Journal, and it kind of gives us a feel for the density thing. This is the density, and this is the density you want, and you have to get above this PSI, and that means you've got to inject it. So in a field, and you're going to screen fields to do this, you got to have it at least 2,700 feet. That's your critical depth, because you can't hold those kind of pressures at any wells above that. Now, and that's just, now this is approximate too. So this is not a perfect thing, but typically speaking, you got to have it at, and that's 800 meters for the international folks. And you need at least there, so you can have the dense phase down there working for you and producing oil, or just being sequestered in a regular saline aquifer. But this is kind of shows you the volume difference in the densities, but you have to get up to this here state to get there. And what's great about this, it's very easy to inject CO2, because as the density close to liquid, the viscosity close to gas, which is real low, and so it's easy to inject. Now, for CO2 flooders, that can be a harm too, because when they are trying to get immiscible and trying to get a mobility ratio going to produce more oil, the viscosity being so low, it'll finger through, and it won't always capture all of that much oil, which is the reason why they get only 15 to 20% of the sweep efficiency or the oil in place that they can produce. Okay, this is a very important slide. Corrosion mitigation. Okay, if you have water with your CO2, you need to then think about, well, do we need to have better pipe in place? And then too, there's a lot of times that H2S will be associated, especially in some of the plants, with the CO2. We try to clean it up the best we can, but and it is a corrosive agent. But you can, it can create a passivated pair on steel, which is, now this is a good thing. If it goes in, it can create a product that actually keeps it from continuing to corrode. But so it will reduce corrosion from carbonic acid, which is kind of helps you a little bit. But overall, your carbon steel specifications, you want higher carbon content, and in carbon steel favors adherence of protective corrosion products in corrosion inhibitors. Now, you can put those in, and they will also keep your carbon from being, and a lot of them, that's what they use. They use the corrosion inhibitors instead of putting have to create these alloys, which is the next thing where they have to put 3/16 stainless steel, although they do still do that, where they know they don't, they can't put the corrosion inhibitors, that sort of thing. But 13 chrome and Moni, those are other alloys. And I got another slide on this because it's so important. Plating and coating. You can also put nickel. You can also coat them with polyethylene. There's a lot of vendors out there now that have coated pipe, and that's what I'll have to say. A lot of well, that's what Kinder Morgan, when I was with them in Shell, they did that all the time. And then the last was, you want to make sure that it's nitrile and deton, because it will sometimes the CO2 will go into these elastomers that they're not made for CO2, and they will cause them to harden, and then they'll no longer be good seals. Injection of corrosion inhibitors, I've talked about that. And then of course cement, you want your cement to be a cement that will not degrade with time with the CO2. Okay, CO2 compression. This is what I want to kind of just show you. This is what a compressor looks like. It's going to depend on the size of your field or a pump. This would be a good. This might be here. Yeah, this here. Notice the compressor, 30 million cubic feet a day compression. It has 5,000 horsepower. But what's great about this is you can, okay, it's real easy to prorate the amount you have in how much compression you need. And it's real easy to do. And usually by the time you get with the compressors, you get the water out. You don't want any water in there. You want to dehy it. And then you want to dehy it after too, I think, at the same time. Okay, I want to talk a little bit about operations, and then we're gonna move on to one other thing. Okay, optimizing the WAG ratio. And what this is, when you inject, and I was telling you earlier about the viscosity, it wants to finger through that producing well. What goes on here is if we start with continuous CO2 injection in your injectors, which this is an injector, and this is a typical 5-spot. Then you inject water with the CO2 to remain within, it all stays in the facility and CO2 supply limits. But then you inject CO2 in water separately, but it's called WAG. It's WAG alternating gas injections. That's why it's called WAG. And you inject it, and what it does is it keeps the CO2 from wanting to finger, and it forces the CO2 to have to go back and get the oil in the ground. And it's been great for you. I mean, some of these operators have put as much as 2 pore volumes of CO2, and they can produce much more oil. And when we first started doing this way back 30 years ago, we didn't, we thought, oh, all you need is a 10% slug. No, actually, you can inject as long as you have the right economics on the producing well. You can get a lot more oil out of the ground with CO2. It both improves your vertical and aerial sweep. Artificial lift, very important for CO2. Most of the time we like to use gas lift, but we do use also beam pumps. And it depends on the location, also probably size of your field and how fast your rates are. There's a lot of things going on. And then, but then the remedial work, you got to lower your pH, and you got to put phosphonate inhibitors, and you got to be concerned about paraffin in asphaltene deposition. Because what happens is when you're on CO2 flooding, right near the well bore, you'll see a pressure drop. And whenever that pressure drop occurs, you're going to see precipitation of asphaltenes. And so it's just, but then what we don't want is CO2 breakthrough, and that's why we do WAGs. But we also have used cement squeezes if we don't want it to go in this part of the zone, we want it to go in the oil bearing zone more. We don't want any of that CO2 going anywhere else. Polymer gel squeezes were wonderful for us in the sack rock field. And I mean, we're talking, we put thousands of barrels of the polymer gels in there. And there's an SPE paper on that if you guys want to go out there. Fiberglass liners, but yeah, the gel polymers, we're talking a cost of only like 3 cents per incremental barrel. So it was very polite on the cost factor overall. Production equipment is very important. And what we'll do, and I'll talk about this monitoring, we got to do step rate tests, and we'll talk about this here as we go forward. This is another system that I wanted to discuss. And what it is, all of us engineers, and now regulators will want to be involved in this too. what we've done is put together the SPE has put together a system. It's called a resource management system, storage resource management system. And what it does is it kind of lays out all the there's documents that kind of puts out the Bible on this a little bit, on what terms to use and what this means and what this doesn't mean. And what's great about it is it's very similar to the IRS PMS, which is the PMRS, which is what it is. What that is does all the reserves for the world. And it's worked on the same basis. What's proven reserves? What's probable reserves? What's possible reserves? Well, now we know what's for sure a good place we can put this storage, and that would be the best in capacity here. And I'm going to go to the next for this. The capacity is really where we want to go. And when now these fields that are storage fields are worth money, and because they're a good place to get rid of this CO2 and keep it there. And so we have now a commercial, if it's something like proven, improbable, and impossible, it falls in this category. And then we can go around and look in, and we can start categorizing other fields, and they could be contingent storage. They could be something that we don't have you need a source close and all that. This is where we ultimately want to go, is capacity. But on the contingent storage, it could be that we just don't have all the hurdles for this project to work, and it'll be under contingent storage resources. And then there's you just got plays and leads and prospects with it, which that is like a prospective storage and resources. And then you got a little bit of range uncertainty, which up here it's possible and proven capacity and probable capacity. And so but it's a way we can categorize this and put a little bit of value in and lay out what's really working and what's not, and categorize these on a very similar to what you would do with reserves in the oil fields. And over here you can see we have a low estimate, which this would be proven, because 90% chance that this is going to work, and usually it is, and usually it does. It's a lot higher, that's a lot better, higher probably than that. But then a 50% chance is your best estimate typically, and that's probable. And then in your possible, it could be we can get there. We just don't. We only think 10% is probably going to get there though. That's all we know anyway this time. 45Q tax credit. This is as of January 2021. January 21st. I think it's 31st. I'm sorry about that. At 21, it could change, and it's already changed several times, and that's why the sequester credits increased. Now this is for saline. I think now it's actually $80 per ton, but sequester credits for CCS has increased from 35 to 50 tons at that time, and I think it's $80 now. EOR credits increased from $23 to $35, and I think that could be $35 now. But this is where I got from some well-qualified people, so I put it in here. I actually got it from the Internal Revenue, this thing right here, if you want to look it up. And but the construction must be started by January 1st, 26. Now, 24 was in the past, and it's changed. And so I think it's going to change. It'll probably change annually, these numbers. But I just wanted to give you one that I knew of at one time was given to me, and I felt good about it. And you do, though, after your facility is placed in service, you have 12 years to use it under this 45Q. Class 2 is your oil and gas fields that are being produced, and you're wanting to go in and use EOR, CO2 flooding. And their primary, you have to qualify under a Class 2 permit, you are primarily focused on protecting drinking water. Now, I've already told you, a good CO2 flooder, they don't want it to go out of zone. They don't want it to go in other zones. They want it to go in the zone that they produce oil in. And so they put cement plugs everywhere along there, even in Class 2 projects. Now, it's not stated that they do that in this, but the way I'm showing this, but they do a good job, just as good a job, in my opinion, as a lot of the Class 6 wells. And And they should. Construction and operation, they need to have a monitoring and testing ability still though, and that's where the step rate tests, the MITs, all of these tests that have to be implemented and reported on to their people, and it must be to the and that would talk about the Class 2 permit. They have to report all of this, and they have to be financially responsible, and all the way to closure to the plug in the well. So I mean, there's a lot of regulations on this already, Class 2. And I'll talk about Class 6 here, which shows even a lot more monitoring. But I believe, well, I know some projects that are Class 2, and they're monitoring just as intense as I would see Class 6. But that's beside the point. And that's good. That's a good. In general, the APA needs to show that the injectant formation is competent to contain the injected fluids. That's from your separate test. And from and then you got to, well, here we'll talk about nearby wells that penetrate the formation must also be I mean, they must be shown that they will not be letting any of the CO2 plume go anywhere else. And that is very important, very important. And that's what the operator should do. I mean, that's the prudent about it. The injection well intents in itself during its life and after abandonment does not provide conduit for injected to migrate into, and again, it's just protecting the drinking water reservoirs. But the people that I work with, they are only going to, they go to all intensity to make sure this just stays in the oil and gas field. I mean, the oil and gas formation that they originally put it in. And there's a number of reasons why you have to do that anyway. The list is not, in this list of here, is not exhaustive. So there's more things here. I just wanted to throw out a few of the things that was important. Class 6. Now, what they're focusing on here is what I think, and I got another, protecting drinking water and ensuring long-term storage CO2. And what they're talking about addressing here is they model it, and we got to make sure that plume does not go anywhere else but where we want it to go and stay in that formation. And this would be for Class 6s for like going into saline reservoirs or other reservoirs that you can place this CO2. And you got to make sure that your corrosion is not going. I mean, with water is not a problem, and you got to show that with either inhibitors or you got to show it with the right pipe. And large anticipated injection volumes. I'm sorry, I thought I did a spell checker on this, but anyway. And okay, requirements are very important. You got to have an extensive site characterization requirements. Construction materials must withstand contact with CO2 over the life of the project. Monitoring and testing, and that's going to be the next slide. I'll show you what we do in monitoring and testing. And you got to report. Some entities require reporting at least every quarter. And it can go up from there. And there is another one I'm not going to talk about. It's a California a system that is also it's market driven, and it is Class 6 intensive for even oil and gas fields. I mean, it's intense, and it should be. It's good. Financial responsibility here. You can see enclosure. Monitoring and testing, MIT is very important. What we're doing there is we're pressure testing the casing, tubing, and packers. That means if you have intermediate string and all that, you want to make sure that all of those are secure and you put pressure on them. And if they don't hold pressure, you got a problem and you fix it. And I think we also inject temperature logs. And in noise logs, what they are is that's similar to an echometer for the oil and gas guys out there. And temperature, though, you can find out where your fluid's going and where it's not through temperature logs. Operational testing, you want to always be doing material balances, where you're injecting. Now, how come if you have a closed system there in the formation, you make sure you can do a material balance and know that, hey, my fluid's staying in zone, and you can do the production and the injection and keep those material balances on target, that you know that you're not losing CO2 anywhere. Injection rate testing, that's so you don't frack the well. So what they do is they go in and all these just good prudent. Before we were getting any credits, CO2 flooders did this every 6 months because it changes your your frac rate changes with the pressure in the reservoir. And so you got corrosion monitoring, which is coupons and casing inspection logs. And then you do pressure fall off. That helps at least every 5 years here. And monitoring wells in the first way in the permeable formation above the combining zone. Why would you want to do that? So if the pressure starts pressuring up in that one above where you're injecting, you don't want that. And if you start seeing that, then you got a problem. And you got to figure out how to. But this monitoring is so important in the aspect of understanding that your CO2 is going where you want it to go and it's going to stay where you want it to be. Plume and pressure front. This is from modeling a lot, and you use all the pressure monitoring wells in the injection zone and outside the injection well to do it. And then also we have surface air and soil gas. And that's sometimes, but what's great about it is you can measure the surface and see if there's any hydrocarbons in the surface, or you can measure gases that and do see if it's increased some places than others. You can do a lot of things. This here's another what we just talked about. But I wanted to lay here what's important here, and especially in class 6, class 2, like I said, operators I work with, they do this too. You want a good cement across all the zones. Up and it should be 100 feet if you can. Depends on the zones, and to make sure that this is an isolated well that will never have problems with any of the CO2 going into the air. And this is plugging. You got to do a final external MIT normal plug process, and you got to make sure that cement is properly it's proper for it's not going to erode from the CO2. And then you need a monitoring system for at least 50 years throughout the system, just to make sure that none of this is happening. No, you aren't losing CO2 outside that plume. And then site closure notification, and you want to make sure that there's not going to be any endangerment going forward, and that all the wells, plugging of the monitoring wells are in good state and in good shape. Okay, I'm going to now really quick, because I only got about, I don't know how much John's going to let me have here yet, but I got at least another 10 minutes, I think, here. Roadmap in EOR evaluations for CO2 flooding, CCUS. And what you do is you go in the basin, you look at all the different fields, you try to screen them, you get their characteristics, then you want to go down and you go through it. We're going to show a screening criteria for these fields. You want to make sure you have wellbore integrity. And so if you go into a field, if you have a bunch of old wells there that you don't think are going to hold, you must go to the next field, because you aren't going to use that for CO2 capture. Or if you can plug them by the regulators, under the regulators restrictions, then you're probably fine. But it's a lot of work and money. So you want to really evaluate the wellbore integrity issues of the current older producers. Conduct an economic analysis, including the gas. And you've got to lay all of the different systems up, and it's going to depend on the rate that you have. And I just got through going through this. To do this right, to give the presentation where you guys would have information to be able to do this, it would take at least 2 to 3 days of workshops. Because the costing, how would you cost all that out and come up with the proper costing so you could do economics? But I'm just going through a high level here and talking about, and then you wanted to have a good CCUS application, and you got to lay out a monitor, recording, and verification plan, which we talked about. And operators have been doing this anyway, but they're going to be sending those reports in and send them to other people, and where they did it just by themselves in the past. Screening of reservoirs depth, we talked about it. I said 27. That was a rough number. We always said 3,000 to 7,000 feet. That's how deep you want these fields to be, so you can go in and sequester CO2. You want them less than 250 degrees. One of the last ones that was near 7,000 feet was 180 degrees. If it still was all right, and it's still one of them I just worked on. But it was higher pressure. We had to get MMP much higher, and it was but it was great project. Oil gravity. We say here 27 to 30% higher is, the higher is better. 40, I think, yeah, with SACROC, when it's a big CO2 flood at Kinder Morgan, it's 40 API gravity. And you do have the dimmer unit, which Oxy operates. I think it's in the middle, lower 30s, but they work. Viscosity and the residual oil, the higher, the better, the residual oil. That's it. When you, after your water flood, what is your residual oil? Saline and gas screening is green and very similar, to the critical state, and you just put it in the ground. But yeah, in saline and gas reservoirs, you're going to want at least 3,000 feet to 7,000 feet because of if you have to pump it in further than lower than 7,000 feet, you got it. The temperature of it just doesn't work very well. It's okay. What are the first considerations in screening? Distance from source to pipeline, and where are you going to go to sink it? Miscibility. If you want to do a CO2 flood, you got to have miscibility in most cases. Now there are immiscible cases. And one was we did it in Kinder Morgan. It was at the Yates field, but it was a top-down flood, and it worked very well, very efficiently. Heterogeneity is important, and then lease considerations. You got to own the field. You got to make sure that the land rights and the land and you can sequester this, and you aren't going to have any people going after you. This is for immiscible flooding, and here's where I was saying you can do this, but if you want it still deep, but if you can do a miscible flood, you can still produce oil. And so that's kind of what this slide's all about. And I'm running a little late, so I'm going to keep moving here. Minimum miscibility pressure. It is the pressure at which the CO2 wants to be miscible with the oil. And if you, what they do is they do slim tube test, and you can see the pressure, and they change the pressure and run a productivity, how much they produce from the slim tube. And they do that until they reach this level line. And once you reach miscibility, you no longer get higher recoveries. And that's the MMP. Down here, I have another slide comparing it to nitrogen and methane. So if you think you can go in and inject methane and do a miscible flood, you can't, because the pressure is so much lower down here. Actually, methane mixed with your CO2 causes the MMP to go up. So it's important, yeah, that and you understand that. These are some of the factors in IRR. The biggest is oil price, and right now we're kind of on the borderline from some of the, well, depends on how close again the pipeline is and all that, but we're on the borderline right now, even at $70, and I got a slide on that. Anyway, this chart is for a $50 per barrel oil case, and you can see the difference in incremental rate of return you'll get depending on the oil price, the operating cost, but G&A and CO2 and capital. So you can see that the most important for a CO2 flooder is oil price. And then there is a slide, and if you guys, you can get a hold of me, I can send you this here. It's a spreadsheet, and it works very well though. It's based on dimensionless curves, and you can use it, and you can put in your drilling cost, facilities, pipeline, your operating costs, CO2 costs, electrical, preventive maintenance, and then your pipeline costs, it's in there, and it's usually on a basis of like, it's used now. It's about 100 to put a CO2 pipeline. It's over 100,000 per inch mile, but that's kind of where we are here. Thoughts I want to leave you with. Good. I still have 10 minutes for questions. CO2 floods have long payouts. They do, and so don't be surprised even when you are doing this and sequestering CO2 and maybe in getting these credits. You aren't, it's still going to be a long payout. And I've said $65 per barrel. This year's probably a year or two old. So I think we're right on the cusp right now of on a typical field and on an average distance of pipeline where you come from your source, and how much that source, how much they're going to let you have of that carbon credit. CO2 floods require large capital commitments, huge. And this is just not a real simple, incentives like 45Q could push projects over the goal line if capture and transportation costs are low enough. And that's, I mean, it's because the person that's also sequestering at the plant, he has to build separation equipment, and he has to build compressors to get it to the supercritical fluid. He has to put dehy plants in to get rid of the CO2. I mean the water, and so it's costly. There is science behind this. There's 50 years of science, probably longer than. In 1952, a patent was issued, and in this book that we have now, Practical Aspects of CO2 Flooding. You can get this out of SPE, and it really is the Bible for practical CO2 flooding. And so if you want to get more info, this is another one. And I usually when the SPE sends that to you, they send you that program that I'll send to you too if you want to email me. But I'll let you, what it is, it's a spreadsheet that helps you, but you need to learn about the spreadsheet, make sure you're putting the right stuff in. But you can get a little bit of a feel for how much, well, if this is a good carbon capture project or not, economically speaking. And that's it. I'm ready for questions, John.
Well, thank you. That was fascinating. You covered a lot of ground. So thank you. That was fascinating. You put like a master's course together there in an hour. Thank you.
But here again, anybody that has questions, off, not today, or get with me, and you can, you guys can post my email. I don't care. And actually, it's on the it's on the Interstate Oil and Gas Compact Commission webpage too, because what I'm one of the gurus for this in there, and so I've told them they can put my name up there for all regulators to contact me if they want more info from me.
We do have a couple questions, Lanny.
Okay, good.
The first one I found though was in the chat, and it's from Mark, and he makes a comment, and I think you covered part of this as I reflect back on your presentation, but I'm going to read to you what he says here.
Okay.
That CO2 pipelines and transportation requires much higher pressures and energy than natural gas, so all new pipelines will be needed. And he's asking, is that correct? Is that
yes,
correct?
That is correct. We always want to, we want CO2 pipelines that will handle the dense phase. Yeah, that is a for sure thing. And if you ever building up for any project like this, you would want it to be a CO2 pipeline, which means, and it's much higher than a gas pipeline. Gas pipelines tend to, their pressure rating, their highest pressure rating is 700-800 PSI. And it could be higher. There's pipelines that are higher than that. Don't get me wrong there. But most of them aren't, and so you would not want to try. Now, and I mentioned that because this one company, but they had a 20-incher, and they were only putting a little bit of CO2 through it. So we looked at it, and it passed the mustard to be able to still transport it in that. But they only go up to 700 PSI when it's got an 800 PSI rating. So I mean they're able to use that. But then what the bad thing is, they can't put too much through it. That's what really comes down.
Mark also makes a comment about CO2 pipelines and storage releases that can cause detrimental effects on local populations. And he references an event in Mississippi also.
Yes, and you're absolutely right, Mark. And so that's why we need to have monitoring systems that if there was ever a release, that the operator know immediately and shut everything down just ASAP. I mean, and of course, PHMSA handles this. These are the regulators at PHMSA, and they make sure, and they also are and it's a smart thing to do. They have us put pigs in the line, and literally those pigs they can tell you within an inch. I mean, where if you're having any corrosion or any metal that's getting thinner, it will tell you that. And so we have to have that done. I don't know the exact rules, but I imagine every couple of years to put through those lines just to make sure. And then if one does show some bad, then you immediately, but we know from those pigs, they're excellent technology. We know where we have to dig the line and where we have to repair the pipe. What's great about it is we've not seen a lot of, there's been breaks, but it's not happened a lot. I actually wish when I was at the last ILGCC conference, one of the regulators put up it was a video of and they did it as a test if a CO2 pipeline ruptures, what it looks like in the kind of problems you can have. And yeah, you've got to be ultra careful. And in terms of in the way the regulators are working on that, I don't think it's something that we need to, lose sleep at night, because we are making sure that that's not going to happen. And then there's a lot of emission technology that's coming out there that you can easily monitor slow leaks. And actually the operators are implementing that along with AI on their pipelines, which is much better than what we've done in the past.
We have maybe we can do some rapid fire here. We've got a couple questions here before we wrap up, perhaps, Lanny, and that is a question that came in earlier on was, does API provide standards for casings used in CCS and CCUS wells?
I don't know. They probably should now going forward, but I'm not sure on that. I'd have to talk to our API people. I just know that, we didn't want corrosion in our pipes, as a field. And you saw that, what things we did in those two slides on the corrosion, and then the metallurgy of the pipe. You have to have proper pipe. You don't want pipe that's going to corrode, because these projects are long-term, and the cost to fix pipe downhole is much more expensive than you want to deal with. And it's a lot cheaper to spend the money ahead of time, if that's right.
Thank you. And Brad says, he says, hey, Lanny, thanks. Great presentation. Do you happen to have similar economic parameters or an Excel model for just pure play CCS projects?
No, we don't, but I don't think it'd be too hard to modify this one. You just wouldn't have a revenue oil stream. And it still has price per well on there, and you'd have to make sure your input's important. And you could probably put that in there in the depth of the well, because you got, deeper wells are more expensive than shallower wells. And you got to get your rates, very important. Most of the problems, a lot of problems where CO2 floods don't work is where they have very tight formations, and then your processing rates are bad. And so then your PV, your present value on the project, because the time value of money just eats you alive. And so I've seen projects that we thought were going to work, and a year or two going into it, we're going, oh, we're going to have to do something, get the processing rate up. And sometimes you can, and sometimes you can't. So, and then of course that last one, there's problems with your asphaltenes and precipitating out, and then you want to keep pressures at the right, so the chemistry works. You don't want asphaltene precipitation around those production wells.
Any thoughts on CO2 EGR?
Oh, well, that's another whole topic of its own. Very important, very important. But I'm not I wish I was more involved in that, but I'm not involved in it as much as I'm more involved in the technical side. But it's very important, very important. Without it, we're in trouble.
And we might be down to the last one, Lanny, that unfortunately you squeeze in. And this person asks, could you go back, please, and kind of explain a little more the supercritical nature of the CO2 and UIC wells? And it goes on, this person goes on and says, the buoyancy and specific gravity are important in calculating maximum surface injection pressures. Right.
Oh, absolutely. What you want, okay. Above that, you have to get in the dense phase. We always stress. And you want, actually, CO2 floaters will put it 500 to 600 PSI higher than the MMP or being higher than that dense phase. Because the higher you are, then you still get, the density plot shows that you do get heavier CO2. The fluid is still heavier at the higher pressure you get. And sometimes that really helps you on, if you're going to, you can put CCS projects in this category too. The higher you are, the more CO2 you can compact in that space. It's the better. And so there is a plot, and it's in this book right here, Practical Aspects of CO2 Flooding, and you can see what the what, the pressure will increase and the density will increase some. It won't increase a lot, but it'll increase some. And you can put it in these water aquifers down below. I don't know. I hope I answer your question. But call me or email me if you want to talk more.
Lanny, thank you. That was tremendous. And we have shorted a couple people questions that they had. And I would just suggest, I guess, you've been very open about your willingness to answer questions offline here. And maybe I'm going out of turn, but I would venture that for you participants that had a question that we didn't answer, weren't answered today, that if you'd email Dr. Schoeling, I bet he would send you back a response. I hope I'm not out of line with offering.
That's perfect. Perfect. I love it. Like I said, I'm on a call 24 hours a day with the ILGCC, and so I'm the guy they call.
Well, thank you. And thanks again for your presentation. You can see it generated a lot of questions and a lot of interest. And for the most part, everybody hung in today with your presentation.
How many participants were out there? I never got to count them.
We had at the mass that I saw about 131.
Wow.
And we hung right there until this very end. So it's great interest. So with that, I thank Dr. Schoeling for participating and for the presentation. For all of you on behalf of TOPCORP, and many of you have met Dr. Hillary Olson at the University of Texas at Austin and Dr. Linda Badalore at the Colorado School of Mines, part of the leadership team of TOPCORP and Top Energy. We thank you for your participation. Keep your eyes out for the next email. We will probably have another webinar scheduled within 2 months or so to keep within our schedule here. As long as we can find willing participants and experts like Dr. Schoeling, we are going to continue this. So thank you for that. I hope you have a great rest of the day, and we'll be with you back again very soon with the next webinar. Dr. Schoeling, thank you, and thank you to our participants who attended today.